Hello, welcome to this presentation on peristaltic pumps and thermodynamics. Today, we will explore how peristaltic pumps operate and how the first law of thermodynamics applies to their function. By the end, you will understand the energy transformations involved in these pumps and how efficiency can be optimized. Let's begin by defining what a peristaltic pump is. So, what is a peristaltic pump? So when we say a peristaltic pump, it's a type of like positive displacement that moves fluid through flexible tubing using rollers or shoes. So these rollers alternately compress and release the tubing, creating a peristaltic motion that pushes the fluid forward. Also ensures contamination-free transfer. So let's look at some advantage of peristaltic pumps. So one major advantage of peristaltic pumps is that the fluid only becomes in contact with the inner surface of the tubing, ensuring contamination-free transfer. So that's what we said earlier. Like yeah, like it ensures contamination-free like transfer. So let's look at some common use in medical, pharmaceutical, industrial and food industries. So like for example in the medical field, it's used in dialysis machine, IV fluid administration and feeding pumps. In pharmaceutical industry, ensures precise dosing and safe transfer of sensitive chemicals. In the industrial sector, it's used for chemical dosing, slurry transfer and wastewater treatment. So there are a lot of applications of peristaltic pump that we can see in everyday life. We can mention a few here since we don't really have much time. So let's move on. So this an image of um a peristaltic pump. Yeah, you can see the fans and a whole lot. It's a very sophisticated uh, machine. So moving on, so why thermodynamics, right? What's the interplay of thermodynamics in peristaltic pumps, right? Because the basic operation, the principles underlying their operations are also principles of thermodynamics. So we can't talk about peristaltic pumps without talking about thermodynamics because that's the principle underlying their operation. So we need to understand thermodynamics when discussing peristaltic pumps. Thermodynamics Thermodynamics is essential because it governs energy transformation within the pump. So some of the key thermodynamics aspects include energy conversion. Electrical energy from the motor is converted into mechanical energy to move the fluid. So that's the energy conversion. We also have the heat dissipation. So that's when friction between the rollers and tubing generates heat. We also have the efficiency analysis. That's like trying to understand energy losses, which can help in optimizing pump performance. We also have the first law application. That's the real, like the main deal here. Also helps quantify the energy input, the output, and losses, ensuring that energy is conserved. So moving on. So what was the working principle? Let's take a closer look at how peristaltic pumps work. So first, let's talk about their motion. So the rollers The rollers or shoes compress the tubing at intervals, forcing the fluid forward. So as one roller compresses the tubing, the next one releases it, creating section that draws in more fluid. So yeah, and we have the flow direction. That's the direction of the fluid depends on the rotation of the rollers. This means the pump can be reversed to change the flow direction. So let's look at some of the advantages of peristaltic pumps. So one is the pump does not allow contamination, as the fluid only contacts the tubing, like you can see in the diagram. It contacts the tubing. It is also self priming, meaning it can operate without being filled first. So moving on, let's move on to slide. Let's take a look at some types of peristaltic pumps. So we have the tube pumps. They are compact and designed for low pressure applications. They are commonly used in medical and laboratory environments. We have the hose pumps. They are built for high pressure industrial applications. They are capable of handling abrasive and viscous fluids. So additionally, peristaltic pumps also operate in two flow variants. So that's their flow variants. You have the continuous for smooth flow, discrete for accurate dosing. So let's move on to the slices where we talk about the components of a peristaltic pump. What's the individual tools, or devices that makes up the whole pump. So to understand energy transformations in peristaltic pumps, we would need to examine their main components. So we have the flexible tubing. That's the it's made of materials like silicon, tigon, or beton. The material is chosen based on the compatibility and flexibility of that material. You have the rollers and or shoes. So these compress the tubing to push fluid forward. More rollers provide smoother flow but increase friction and energy loss. So there is this trade-off also there. As you provide smoother flow, it also encourages energy loss. So yeah. So we have the pump head, which houses the rollers and tubing, ensuring proper alignment. You have the motor and drive systems, which converts electrical energy into mechanical energy, or into mechanical motion. Some pumps allow variable speed for adjustable flow rates. That's some pumps. We have the control units, which regulates motor speed and flow rate for precision. So let's actually examine the main thing. That's the first law of thermodynamics in peristaltic pump. So these are the the diagram. Yeah. So what does the first law says in how does it apply in peristaltic pump? So the first law of thermodynamics says that energy cannot be created or destroyed, but can only be transformed. So applying this law to peristaltic pumps, right? Energy input, that's the electrical energy from the motor, is equal to the mechanical work that moves the fluid. So there are also some losses like heat, that's the heat from friction. But when two bodies are in contact and they are moving against each other, there is this heat that generates. So it's a loss to the peristaltic pump. So That's the heat generation due to friction between rollers and tubing. So this is the equation. Change in internal energy cause the heat minus work. Heat change minus work. The reason why work is negative is because work is actually done by the system. So moving on, let's talk about energy flow in peristaltic pump. Right. Let's talk about energy flow in peristaltic pump. So the energy transformations in peristaltic pump follow follow this sequence from electrical energy to mechanical energy. That's the motor converts electrical energy into rotational motion, and then we move on to mechanical work to fluid motion. That's when the rollers compress and release tubing, displacing the fluid. We also have some energy losses here. That's like as we said earlier, the friction between the rollers and tubing generates heat, right? And then there is also electrical resistance in motor, which is a loss because it affects the efficiency. And then we have the internal fluid friction. That's the friction between the fluid itself, more like viscosity or something, which also adds to the energy loss. Because if the fluid is highly viscous, then I mean, you need more energy. So let's move on to the heat generation and dissipation. So heat is generated in peristaltic pumps due to frictional heating. That's the heating between the rollers and tubing. We have the electrical resistance in motor. That's yeah, in motor windings. We have the internal fluids. That's like we said, fluid viscosity also affects heat. Like it adds to the heat generation. And we have the dissipation methods as well. So to manage heat, that's what the dissipation method is all about. To manage heat, cooling methods include the air and water cooling, that's natural or forced convection. We also have the heat resistance tubing and proper maintenance and alignment. So all these things are to manage heat, or their cooling methods, like methods to cool the fluid so that we won't lose energy. So moving on, efficiency considerations. Right? So we have factors like it's a machine, so definitely the the efficiency wouldn't be 100%. So here we are going to look at some of the factors that affect the efficiency of the machine. So tubing material and roller design can affect the efficiency of the machine. That's softer tubing increases friction and heat. So when the tubing is soft, there is that friction between the tubing and the rollers, which adds to the heat or which increases heat. We also have the motor power and speed. That's high speed operation generates excess heat. Yeah, that's obvious. So what are some of the improvements we can do to reduce some of these to make the pumps more efficient? So some we can use the low friction tubing, can use energy efficient motors, and then also proper cooling and insulation. So these are some of the things we can do to improve the efficiency of the machine. So this is the last part of the presentation, which are which talks about some advantages and limitations. So what are some advantages? Like we said in the first slide, it's contamination free operation, right? It's also self-priming and dry running capability. It handles viscous and abrasive fluids, and these are some of the limitations of peristaltic pumps. So it has special limitations, right? Also, it has that pulsating flow. That's like, I think turbulent, more like turbulent flow or something. It's not smooth. The flow in the tubes are not smooth. And then there's also this where tubing wear over time due to friction between the tubing and the rollers. So what are some of the real world applications? Like we said earlier, it's used in medical dialysis. In medical field, it's used in dialysis, IV fluids, feeding pumps. In pharmaceuticals, it's used in dosing sensitive chemicals. In food and beverage, for hygienic transfer of sources and fuel. In the industrial sector, it's also used in chemical dosing, wastewater, and so. What are the key takeaways, right? So to summarize, peristaltic pumps efficiently convert electrical energy to mechanical work. Yes, that's the best. And then also the first of thermodynamics explains energy conservation in these pumps. Heat generation and efficiency can be managed through design choices, like we said earlier, like the tubing, making the tubing more harder instead of softer, because when it's soft, it increases the friction, which, yeah, adds heat, more heat. And also, you have